And then I share the screen. And I close the window. So we continue with this sequence of talks. Last time we were speaking about tropical caustic in the unimodular case, and today we continue and we'll speak about more in greater generality, namely for tropical caustics for general admissible domains, and I'll tell a few words about the recipe for constructing the caustics in the non-unimodular polygonal case. So yeah, so I repeat what we are dealing with. We are dealing with closed convex sets with a non-empty interior, and now for every integer vector we define CV as the infimum of the linear function with the gradient v on our omega. So of course it can be minus infinite. Yeah, if your domain is compact, then it's always finite. And now we denote by a omega the set of all such integer vectors that have a finite infimum. And we note that 0 always belongs to this set. No, it's not AV, it's a omega. And the claim that we made orally during the last week presentation was that omega is admissible if and only if this set A omega contains more vectors than just 0. And this is not...
Recall the definition of admissible very briefly.
Yeah, admissible is something that doesn't contain a line with irrational slope. This was one definition. Like having a line with irrational slope immediately violates this infimum. So like any function with integer gradient would be unbounded on a line with irrational slope. It would be unbounded from the both sides. So the supremum would be infinite, infimum would be minus infinite. Is it clear?
Yes, yes.
Because a line with a rational slope line. So let's say v defined by PV equals to 0 will always intersect a line with a rational slope. And going along this line with the rational slope, you will get as large or as small as possible. So you're not bounded. So yeah, that's one implication. Other one, it's not that hard. Anyway, so you can take it as a definition of being admissible. Admissible is something which has some support function. So this CV basically it guarantees, if it's not infinite, minus infinite, it means that you can cook up a support function from this linear function and CV, making an affine function which takes 0 at some point in the boundary and is non-negative otherwise on your domain. Okay, so an omega tropical series is a function such that it takes non-negative values, and which can be written as an infimum of this tropical monomial AV plus P times V, where V belongs to subset A. So A is potentially any unbounded, so infinite subset of the square. And you can think of this expression infimum AV plus PV as an analog of a potentially infinite Laurent polynomial, Laurent series. Okay, one maybe not even necessarily Laurent, just polynomial series. So yeah, and what's crucial in this definition is that the restriction of f to the boundary is 0. And then a corner locus of such function, so basically the locus where this function is not smooth, is called an omegatropical curve. And we also can add analytic in a sense that it's not necessarily algebraic curve. Algebraic or non-analytic would mean that your series is actually a polynomial, it's finite. Okay, and now that's the theorem that I'm not going to prove, but it's an easy thing. I'll mention a sketch maybe of the proof that a domain with a closed domain with non-empty interior is admissible if and only if there is some omegatropical series which is not identically 0. So that's why we like admissible domains, because they have some tropical series, and like to mention it, all the limiting toppling functions from the sand piles will be omegatropical series. So that's why we like them, and that's how we learned about this omegatropical series. We learned them from sand piles. And I'll tell...
Just a second here. Here it's tempting to try to ask a question that I don't even know how to ask. Just like tropical curves are analogs of classical curves, algebraic curves, or analytic curves. Here, this admissibility condition, one would like to ask, what is a classical analog? I don't even know how to ask that question.
Oh, yeah. So basically, on non-admissible domains, from the sand pile perspective, you would have troubles. Even perturbing at a single point the maximal stable state would result in a very large number of topplings. So admissibility, in a sense, it's where the relaxations are more or less tame. So, for example, on this strip with a rational slope, it will be much bigger. You will lose much more sand than on the strip with a rational slope. So this is like where it comes from. Sand pile, classically, I have no idea. So, like maybe one thing I can tell you that this omega tropical curve is some piece of the tropical curve that can be completed to a tropical cycle by adding the boundary of your domain. So when you do this, for example, follow what I'm doing, you do this. Like you have a rectangle or a square, I don't know, and what you say that what's inside is this omega tropical curve, and omega is this square or whatever. You say that you introduce negative multiplicities for the boundary. So for every side, you take multiplicity -1. Then this guy will satisfy the balancing condition, even at the boundary vertices. So this is another way of seeing what does it mean to be omega tropical. That your curve can be completed to a tropical cycle by adding the boundary with negative multiplicities. Okay, and that actually explains why this tropical symplectic area of this omega tropical curve can be computed just from the boundary. It will be just the omega, the symplectic area of the boundary, because it's invariant under deformations. Okay. Okay, I continue. So that's actually how we prove the thing we introduce for an admissible domain, a particular and in a sense best tropical series which is just an infimum of all support functions of this domain. So remember, this CV was the infimum of a linear function, and if we add minus infimum to this linear function, we get a function which is non-negative on the whole domain, and it's zero at some point where it supports our domain. And so this omega tropical series, what's important about that is that we remove zero. It doesn't contain the constant term. And we've seen this series in the form of polynomial for these unimodular domains in the previous example. Okay, in the previous talk. So the claim is that f omega is a non-zero omega tropical series. So, and this is one application of this theorem that I mentioned. So, yes.
Of course, and this new, let me call it a new definition of the caustic curve. It's more general in that it can be applied to domains that are not necessarily del Sant polytopes or things like that.
Yeah, exactly. It's applied to any admissible convex domains. Okay. So if you like, one can use sandpiles to extend it to non-admissible domains, but there what you'll see, this caustic curve, is stop being a curve. It's a high-dimensional object. So yeah, I'll tell a little bit more about that in a couple of next slides. So anyway, so an interesting part here is actually to prove that f omega vanishes on the boundary. That's a really cool proof. I remember that we worked on that for several days in Oberwolfach, and it was a really pleasurable discovery that you can use the continued fractions to prove it, that it's actually zero on the boundary. And the hardest case is actually when you have a junction of a smooth segment of the boundary with a segment of a smooth arc of the boundary with a segment with a rational slope. That's the hardest case. Yeah. And I think it should be interesting from the geometric perspective, from this generalized toric varieties. Those types of points should be divorced in some sense. When you have something smooth, like this, and then you have a line with a rational slope.
Very interesting, yeah. Of course, continued fractions sounds a little bit like resolution of singularities.
Exactly.
It is very intriguing, yeah.
So I was thinking that I prove it today, but I think it would be too much. That's it's not a hard proof, and I feel that I could present it, but yeah, I've chosen not to in order to maybe tell a little bit more stories about these caustic curves. Anyway, yeah, that's the best example, the only example we've plotted. This is the plot of f omega for the unit disk, and this is some kind of pyramid over a disk.
Beautiful diamond. It's a beautiful diamond.
Yeah, it's a very beautiful diamond. This picture is made in Mathematica, like from Mathematica. So yeah, that's one of the last things I did in terms of visualization in that period. So anyway, so in here these coefficients, those are very peculiar. Those are very simple. Those are just the absolute values of these integer vectors. This is easy to prove. Okay. And if you look at the caustic curve, it's like this. So it's not the perfect visualization. If you look close, there are some yeah, some imperfections here, but yeah, that's I think you understand that it's an infinite tree, and in the middle you have a four-valent vertex, and all other vertices are three-valent and smooth, and the faces they actually correspond to rational points in the circle. Like apparently the rational points of the circle are exactly the same as points where the slope of the tangent line is rational. So that's uh, a nice property that circle
So could
has.
you repeat that? Could you repeat that statement slower, please?
You see the points where the circle, the slope of a tangent line is rational. Those are exactly. Am I telling it wrong? Maybe I'm wrong. Yes. I should correct it. Not rational points, but where the tangent has rational slope. This
Well,
is.
it's the same. It's the same because the equation is ax plus by equals 0 or something like that,
Yeah,
isn't it?
yeah, 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 yeah. I was thinking about non-rationality of the modulus, but it doesn't play a role. Yes, exactly. So that's a correct statement. Yes.
So
Okay.
we have this tree, and this tree, if I travel through this tree and I try to travel in this tree towards the circle always, I will end up at a rational point.
Yeah, you should. You end up and you go tangent. So you go tangent to the circle. You get closer and closer to the slope of the line tangent at this particular point.
So, but this is very interesting in many ways because if I try to number these points by set theory, uh, first I have four options. So I start at the center always. So I have
So
four
you
options.
see, you go to irrational points. So rational points are not. No, they have kind of. Yeah. So each
It's
domain
uncountable.
corresponds to a rational point.
Yes, exactly. But travel meaning that you go right, go right, go right, go right, go right. In this sense, travel. Well, if you interchange left and right randomly, then you can approach any point whatsoever.
Yeah. So in this case, you can approach any point, not only rational but also irrational.
But if your sequence stabilizes, if you either go only left or only right, then you approach the rational points.
So, but let me ask this. This is very interesting. This is extremely interesting. So the limit points of this tree is the whole circle.
Yes.
I can reach any point in the circle by, well, this is set theory, you know. Now let's go. We're talking about set theory. So let's just take half of the circle. And clearly, the paths in half of the circle, clearly the paths are in one-to-one correspondence with the binary expressions 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, infinite binary expressions, because at every vertex of this tree, I have two options. It's a binary tree, and it's an infinite binary tree. So I have an uncountable number of paths going towards the boundary. And then I can reach absolutely any point in the boundary, right?
Yes.
And if I give you the sequence, if I give you the sequence 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, etc. I mean, I could conceivably just go to a Cantor set, but no, I'm going to an interval. And how hard it is to compute just from the sequence what point I land at.
I don't think it's too hard. I think you can write an explicit formula in terms of some limit, so in terms of some series.
Yeah.
Just a
But
continuous
this is set theory and calculus, I suppose. So we should ask Nikita.
Yeah.
No, it's not calculus. You see, just a continuous fraction. So
Is the continuous fraction expansion of the number?
yeah, exactly.
I'm not so sure that it's exactly that, but I think it's really close to that. It's
Well, it would be very nice to
So you see,
understand.
for each point, you try to approximate the direction by rational line of this direction, and each time you turn left, you turn your like direction just a bit. So, well, I think it's from my perspective just the same as you try to approximate by continuous fraction a given like irrational number. Just do exactly the same.
but going left or right, what does it mean in terms of continuous fraction?
Well, so you see, when you write continuous fraction, you choose x variable and y variable.
Okay.
Yeah, well, there is signs in the continuous fraction. There is signs, isn't it? There is signs. I don't know.
So okay, that's true. Yeah, it's about Fourier series. It's about this Fourier series of rational numbers, and going left to right, it's exactly this thing. It's going deeper in the next level of the Fourier series, I think.
Very nice. Very, very, very nice.
Okay, and how we learned about this curve? But well, the truth is we were looking at sand piles and particularly sand piles on the disk, and this is a result of adding a single grain in the middle of the 100 radius circle filled with all threes. And you see it's very similar, right? Those two pictures. Those are not exactly the same, but there is not much detailization near the boundary, and so that was the moment where contemplating this picture. That was where we got the idea of infinite tropical curves, like tropical analytic curves, and tropical series, and in particular the caustic curve. And, yeah. The white here is as usual 3. The small circles, I think it's 1. Black squares is 2, and I don't see. Yeah, there are also crosses. The crosses are 0, but there are very few of them. Okay. And that's the general theorem that we will be proving next time. So today I just stated, and I don't state it extremely explicitly. There is some things hidden. So for an admissible domain and a point inside, consider its discretization. So for some h greater than 0, you intersect your domain with the lattice with such mesh, and you round somehow this point. And in this particular case, it doesn't really matter how you round. You just choose some point from the lattice nearby this point P. Doesn't really matter which one. Then the claim is that the locus where the relaxation of a perturbation of the maximal stable state at this point differs from 3, converges to a very specific omega tropical curve, which is given just by slicing the tip of this pyramid that we've seen. So we take the minimum of, so we add the constant term, if you like, to this omega tropical series. We want our resulting tropical series to be not smooth at P, and the most obvious way is to actually make it break exactly this P by adding the constant term, which is the value of this omega tropical, this one, of the omega tropical series at P. And the scaling limit of the toppling function will be exactly this minimum of f omega P, f omega Z. And in particular, if P is the point of extremum of f omega, so the point where the maximum is attained, then the deviation loci converge to exactly the caustic curve. So in the case of the circle, this point is the middle. For example, for rectangle, it will be that maximal segment. But anyway, so this is the origin of caustic curves. This is how we learn about them. And those appear as the curves from sand piles. Yeah, so like one thing I didn't tell you in which sense those deviation losses converge to these omega tropical curves. Well, they can converge in the Hausdorff sense, but also in compacts, and compacts are supposed to be contained strictly in the interior of our domains, and that's how we resolve the problem with the boundary. Actually, if you don't do that, you will also have some noise along the boundary, not only the curve, but as in the previous picture, you see a lot of noise, and yeah, actually in this example, the whole boundary will belong to the limit. Okay, and one of the tools we need to prove the theorem in this case is the possibility to approximate our domains from inside by polygons, by the polygons with rational boundary slopes, and yeah. So in the most canonical form, this comes as this thing called canonical evolution. I don't know if it's the best name, but this is how it's called in some places. It's an extension of something many of us played when we were kids. Like you consider some convex polygon, lattice polygon, and then you consider the smaller one, the derivative of it, if you like, which is the convex hull of the interior intersected with the lattice. So you go one step inside. With this canonical evolution, it is a continuous analog of what I've just explained, and it's done just by doing the level sets of the tropical distance function, this f omega. So you take some t greater than 0, and yeah, so t should be greater than 0. And you take the level set of this function f omega, and this we call omega t. Yeah, and this omega t is always a polygon whose sides have rational slopes. This is what we call Q polygon, and if omega has a smooth boundary, then these level sets are actually unimodular polygons. And this is a canonical dynamic on the space of admissible domains. And it's very funny. It represents domains which are not Q polygons as a boundary. It's something which has no past in terms of this evolution. So I tell you a few more words about this. So yeah, why I've chosen to call it canonical? It's because of this wake statement from the toric geometry. So if you look at these domains as moment polygons of toric surfaces, symplectic toric surfaces, then actually this is a very simple equation. There is a very simple equation which tells you how this evolution works. The derivative of the symplectic form, or rather the class of the symplectic form, should be the canonical class. So this is the evolution which is defined by the canonical class of the toric surfaces. Is it clear? It actually shouldn't be clear at all, like where this equation takes place. It's one question, but yeah, it's...
This equation, I assume that this equation takes place in the Kähler cone of the variety.
Yeah, but of which variety? Because the varieties also change.
The varieties change by blowups, don't they? Or?
Yes, exactly. Or as a blowdowns. When you go along this evolution, you do blowdowns. But that's the reason why I've chosen to call it canonical evolution, because it's canonical class driven. Yeah, it's a flow which is parallel to the canonical class. Okay, so...
But as you say there, it happens in cohomology, and this cohomology doesn't change with these blowdowns, do they? Does it?
No, no, your cohomology gets smaller when you do blowdowns.
Yeah, but by then you are inside this part of the cohomology. By
Yeah,
then
yeah,
you are.
yeah, exactly. So this is how you make sense of it. So yeah, yeah. So it happens in the Durand cohomology, and yeah, for example, you can stay in the same variety, and you can relate the cohomologies of different varieties by the pullback of the blowdown.
Well, this has perfectly good meaning. This is a differential equation in the modular space of toric varieties.
Exactly, and this is how you think.
In our modular space of toric varieties. So this is a path in our modular space of toric varieties.
Yeah. And so now you may wonder about a few things. For example, so the future is easy. The future is always that thing is constructed to a segment. But what's about the past? And these are a few things you can say. So a Q polygon. So if it's not a Q polygon, it has no past at all. It's clear. Because the non-trivial levels are Q polygons. But if it's a Q polygon, it has a path if and only if that the singularities of the surface are relatively mild, which means that they are AN singularities. And AN singularity, you can think of it as a contraction of a chain, of a linear chain of -2 curves, -2 self-intersection curves. Okay, so it has infinite past if and only if it's in a sense del pezzo. So more precisely, if its anti-canonical class is numerically effective. And these two remarks, they become easy to understand by the last remark. If you analyze what happens with a particular side. So what is the speed of change of the side during this evolution? So I take some side of a Q polygon and the corresponding divisor is D. And for t greater than 0 but still small, I assume the small deformation of this side, which is the side of this omega t. And then I look at the derivative of the length of this side. And then I can compute it simply as using this equation as the product of this divisor. So I should either erase S here, so I erase S here. It's divisor of this side S. So, and you have this minus d square minus 2. And this is why actually the minus 2 curves matter. Because those minus 2 curves are exactly the curves which doesn't change their size during this evolution. Because minus d square minus 2 equals to 0. And this is why AN singularities actually correspond to the multiple edges. So this may, you probably don't understand this from formula, but let me show you the picture. That's the picture of about the resolution of singularities. So you start with the triangle above, and you see it has no past for very severely because of the B and C corners, and it has two edges which are multiple, like 3 and 4 multiplicities. And I've shown how you do the resolution of these singularities. So and this pink highlights, it shows the -2 curves. And -2 curves are exactly the curves where these edges which enter the corners, which are the vertices of these edges, the edges should be parallel. So which means that the corresponding side doesn't change speed when you do the evolution. Okay, so I'm going too slowly. So anyway, so does it make sense or
It makes sense, but I disagree with you going too slowly. For me, you are going horribly fast. But it makes sense. It makes sense.
Yeah,
It
just
makes,
yeah.
but let me slow you down a little bit and ask here. In this one example, could you? I understand I understand kind of every piece, but I don't understand what's the point of the example.
The point of this example to illustrate what is the relation of the singularity of being n, singularity an, and of the multiple h. So you see that the nh of multiplicity 4, for example, is being resolved to 4 edges which are parallel. And those edges which are parallel, they are adjacent to a side which doesn't change its size when you do the evolution. So this is like an attempt to explain why at all these an singularities appear here. They appear because there are -2 curves, and -2 curves, those are exactly the curves which doesn't change their speed during the evolution.
Okay.
Yeah, so I'm in this talk, I'm not proving anything. I'm just, trying to show different sides of this story in this limited amount of time. So one more thing you can learn from this picture is actually how you draw the caustic curves for non-unimodular triangles, the triangles with vertices A, B, C. So the recipe is that you need to draw dual cones to the corners. And you need to analyze the basic geometry of it. So I'm not going there, but it's fun. I used to like it a lot, drawing these caustic curves for non-unimodular triangles. And I think it's something unexplored. So there is lots of geometric structure there, but I'm not going there today. Anyway, so let's go. Let's wrap up. So one more thing I wanted to tell you. I wanted to tell you about these formulas for the area and perimeter and so forth. And for that, I need to introduce the minimal model of an admissible domain. And this is a very easy thing. It's just obtained from your domain by removing all non-maximal vertices of its caustic. So yeah, I'm not going to explain it too much, but for example, for a circle, this minimal model is a square. And then a circle can be actually sculptured from the square by corner cards, which are symplectic blowups. Sorry. And now I just show you the formulas. So I'm going really fast here because we actually don't need it at all for what comes next for this St. Palach theorems. It's just a nice bonus I really like and I just want to mention. So these are the formulas. So this is not all the formulas we have. This is just some of the formulas which are actually SL2Z invariant. So you can compute the perimeter, the integer perimeter, you can compute the area, and you can compute the action as some series of powers of these collision times from the previous talks. Or otherwise, it's the values of this f omega series at the vertices of the caustic curve, of the non-maximal vertices of the caustic curve. So another way to approach these formulas they can be seen as some kind of localization formulas. So for example, an integral of 1 over the domain, you localize it to the vertices of the caustic curve. And you can have an intermediate step in this localization. For example, you can compute the area at the integral of
but localization under which action, so to speak?
Gradient of I think it's a gradient. It's the gradient of f omega itself.
In this flow, with the canonical class.
Yeah. So I'm not going to explain it today, but you can do the formula not as an integration over vertices of the caustic curve, but over edges. So this is also really fun. So anyway, and to show you concretely what these formulas give in some particular cases. So yeah, I was in a rush preparing these slides. Sorry for handwriting, but these are the above the two formulas for the disk. So you do these defects in the triangular inequalities for the matrices in the positive part of SL2Z. So one gives you 2, the squares gives you 2 minus pi over 2. This is the area. Similar formula for the area of parabola. So we have never written down, but we certainly calculated the perimeter, but I couldn't find it and I had no time to actually redo the computation. Anyway, and the most peculiar of all these formulas, I find it is actually for the triangle, the right triangle with one irrational hypotenuse of the slope minus alpha, where alpha is positive. Those are really funny looking formulas for alpha in terms of continued fractions. So I don't know if it's useful, but I like it aesthetically. So especially
Nice.
yeah, those are very similar formulas, but introducing square makes QU1. So why? I have no idea. And actually, how we prove these formulas, those are proven geometrically just by corner cuts from this bigger polygon going to the smaller domain. And yeah, I'm not going there. Maybe in some future we will speak more specifically about these formulas. But as I told, understanding these formulas is not needed for the last couple of talks. Next time we will proving the convergence theorem for one-point perturbation. Okay. Any questions?
Well, I have many questions, but I'll ask them more privately because it's a beautiful story full of very interesting details that I have to absorb, but it's fantastic. It's very beautiful. Thank you very much. It's very nice. There is a raised hand somewhere there.
So I start
My
recording.
hand. I'm on raising.